this video, I want to show you how to use this table down here to determine the orders of these reactants in the kinetics experiment we did yesterday. But I want you guys to use this table and show your calculations down here. I have some algebra set up here on what you're going to do, but let's start by taking the molarity ratios and the rate ratios of each of these reactants. So for the peroxide, we're going to use trials 1 and 2. And so, meaning we're going to divide the molarity of the peroxide for trial 1 divided by the molarity of the peroxide for trial 2. So we'll go up here and find the peroxide and divide that by that. So that's 2. And we're not going to do autofill. And then we're going to get the rate ratio. So that means we're going to go up here, be consistent, do 1 divided by 2. Okay, and then the algebra, and I have these values set up here. But this calculation that we're going to do right here is going to be the same for the iodide and the H+. So isolating M, we could take advantage of log base 10, so we'll take the log base 10 of 1.5 and the log of the right side, and that taking the log of the right side allows us to bring down that exponent of M in front, so we have M times the log of 2. So now M is the log of 1.5 divided the log of 2, but I'm not going to type in those numbers. I'm going to type in just the cell identifiers. So log, because we're going to do this for the other cells. So log of 1.5, which is the rate ratio, divided by, don't do that, divided, now close the parentheses, then do divide, log by a log of the other one, which is the molarity ratio. Okay, so that's 0.589, and we're going to have to enter values here in order to get some answers, of course. So I'm going to go back up here and get the molarity and rate ratios for the iodide now for 1 and 3. So iodide is here, so there's 1 divided by 3. And then the rate ratio, we're going to be consistent, and rate 1 divided by rate 3. And the order is 1.25 for this particular set of data. And then for H+, we're going to do 1 over 4. You could do 4 over 1, but as long as you are consistent with where you put the rate and the molarities, it really doesn't matter. So I'll just follow with what I have here. H plus concentration from trial 1 divided by trial 4. And then we're going to do the rate ratio from 1 divided by 4. That gives us an order of 0.066 for that. All right, so right here I wrote out the rate law with the orders that I determined. Then I rearranged that equation to isolate K. So now I'm going to use the spreadsheet to solve for the K values at the 3 different conditions or temperatures. The warm and the cool trials were done using the same concentrations of peroxide and iodide. We need to be mindful that the pH changes as temperature changes. So we can't use the hydrogen ion concentration that was for trial 1 for determining the K at the cool and the warm temperatures. We need to use the pHs at those warmer and cooler temperatures to determine the actual H+ concentrations. So everything here looks just about the same with the exception of this term, which is the concentration of the hydrogen cation. See that? And then this term here, which is the rate. So line 53 is for the cool, line 47 is for the room temperature, and line 51 is for the warm. You can see that 51 there. So let's go up here and take a look. So I use this trial here, and so that's line 51. 47 is trial 1 at room temperature, and then trial 7, or line 53 is trial 7, the cooler temperature. These temperatures may not be exactly what were written on the board, but I'm just going by memory. Got the Ks, and now we can proceed and calculate the activation energy. So what we could do here is we take the reciprocal of the temperature in Kelvin and then the natural log of the K values. So the cool was 3, room temp was 24, and the warm was 55. And then these are the associated natural log of the K values. Okay, so before I use the slope function and then calculate the activation energy, I want to see how good these data are. Like, do these data represent a linear relationship between the reciprocal of the Kelvin temperature and the natural log, what the data actually looks like on a graph? Looks like a pretty linear relationship. R squared is 0.98, not too shabby. So I think we could go ahead and proceed and calculate the activation energy using the slope of this line. And so go ahead and use the slope function using the data we have. We multiply the slope by the ideal gas constant, or the negative value of the ideal gas constant, to get rid of that negative. I converted this to kilojoules, divided by 1,000. So our activation energy for this reaction is 38 kilojoules. So hopefully you enjoyed doing this experiment and going through all of this to get to the activation energy.